Thank you so much, Kate, for agreeing to give the seminar. So Kate Selway is a geophysicist, and her main goal, I guess, is to constrain mantle composition. She gained a PhD from the University of Adelaide in 2007, and has since worked in different international institutions, including Yale, the Lamont Doherty Earth Observatory in the US, the University of Oslo, and Macquarie University, where we actually met a few years ago. She is now at the University of South Australia. Quite amazingly, Kate is just coming back from a field trip in Greenland, but I don't know if you're going to talk about that or not. In any case, I think we both even though we're focused on Antarctica, I think we're quite happy to hear about Greenland as well. So Kate, please go ahead.
Great, thanks very much, Laurie. I will share my screen. There we go. Can you see my opening slide there? Excellent. Yeah, thanks very much for that introduction. Yeah, as Laurie said, I'm a geophysicist, and today I'll be talking about how we can especially combine geophysical data sets to improve our understanding of ice sheet behaviour, especially glacial isostatic adjustment and ice melting models. So my particular expertise is in a technique called magnetotellurics, or MT. And so MT is an electromagnetic geophysical method, and it images how electrically conductive the Earth is. And so that's useful for a number of things in polar settings. And two particularly useful things I'm going to talk about today are to image relatively shallow depths just beneath the base of the ice, looking at basal melt beneath the ice and some deeper groundwater systems, but still at relatively shallow depths. And also then the kind of one really useful thing about MT is that kind of with the same technique and even the same instruments, we can see a huge depth range within the Earth. So we can see those depths just beneath the ice and through to hundreds of kilometres into the Earth. So then I'll talk about using MT to look at those greater depths, and then combining especially with seismic data and also GNSS data to improve glacial isostatic adjustment models. So as we go through the talk, I'll explain what I mean about those things. And yeah, and as Laurie said, I've just literally 3 weeks ago arrived back from a massive field trip in Greenland, where we applied some of these techniques. So these are techniques that we will be applying with ACEAS in Antarctica. But yeah, also have been using them to look at really similar questions in Greenland. So so I'll use that as an illustration of what we're doing. And also I have a lot of nice photos from that fieldwork as well that I'll show too. So to start off with, using MT, looking at those shallower depths to look at basal melting and groundwater beneath the ice sheet. And this, kind of to say at the outset, this is a pretty, really, like actually all of the things I'm talking about today are pretty new applications of MT. And particularly this work, there's really one main study that's come out, that's only come out this year actually doing this work. So this is something that we plan to do in the Denman Glacier region. But yeah, pretty new kind of a new technique. So I don't have a lot of examples of my previous work to show for this because it's pretty new. So why do we care about this? So I guess if we think about the ways that ice sheets can lose mass, then surface melting is one of the really obvious ways that they can lose mass. And that surface melting can have a few different effects. The melt itself can run off, it can change the surface albedo and increase more melting through that. It can encourage calving of glaciers and we can lose ice that way. But also that surface melt can drain down to the base of the ice sheet. And then when we have melt water at the base of the ice sheet, that increases its lubrication, and it means that the ice can flow more quickly. So this is particularly important at glaciers, where that surface melting can drain down and increase the flow of glaciers. And we can also get basal melt beneath an ice sheet from deeper processes as well. So there might be some really high surface heat flow coming out of the earth that encourages the base of the ice to melt. Then that meltwater again increases lubrication and helps the ice flow more quickly. And also, just as the ice is flowing, then the friction from that process can melt it and then kind of become a feedback that then that meltwater helps the ice flow more quickly, and then the friction produces more meltwater. So understanding where there is this water at the base of the ice sheet is really important for understanding these ice sheet dynamics, and for knowing regions where the ice might have less stability. Just an example of some work looking at this. So this was some work in Greenland where these surface melt pools were observed, and then they drained down to the base of the ice, and then observations of the ice then flowing faster as these melt pools drain down to the base of the ice. And then I guess another thing that meltwater can do is interact with deeper groundwater systems. So that then once that meltwater is at the base of the ice, it can seep further down into groundwater systems, and then form part of the bigger kind of hydrologic system beneath ice sheets. This is also potentially a way that we could be losing a lot of meltwater that we're not tracking if that groundwater then flows out into the ocean in ways that we don't, and it's pretty hard to measure. So it's certainly a way that it's part of that ice loss system that we're potentially not measuring. So seeing where there is this basal meltwater is really important. And currently the way we mostly do that is through ice penetrating radar data. So radar data, it's essentially a wave that comes down from the radar instrument and reflects off different layers. So it can see layers within the ice. It's really useful for kind of calibrating ice ages and deformation. But then if it gets down to the base of the ice, then you'll get a really strong reflection off a water layer if it exists at the base of the ice. So that's really the bulk of the data that we have to tell where there is this basal meltwater. And so, as I say, this new idea is to use MT to kind of supplement and expand that data that we can get from radar. So MT, as I say, is an electromagnetic technique. So if you're unfamiliar with that, if you can remember even back to high school physics, you may have had a magnet and a coil of wire, and move the magnet in and out of the coil of wire, and you generate a current in the coil of wire. That's really the same principle as electromagnetic geophysical techniques use, that if we have a magnetic field that's changing in time, it induces a current in something conductive. For MT, that magnetic field that's changing in time is actually the Earth's magnetic field. And really because that source field is so big, really, is why we can see to such huge depths within the Earth with MT, and why we can see such a huge range of depths within the Earth. So even at these depths, it means that we can see deeper than radar can see. And you might be familiar with some other electromagnetic techniques. There's a lot of airborne EM that have good resolution over shallower depths, but can't see down to as great depths as MT can see. So if you're on some ice that's a few kilometers thick, even radar might be struggling to get through to see that meltwater at the base of the ice. And even if it can see that, all it's going to do is give you a reflection and tell you that there is water there. But the MT can hopefully see a bit deeper. Well, it can see a bit deeper, and then we can hopefully use that to tell us maybe what the thickness of that melt layer might be. and also then penetrate deeper beneath that melt layer and see if there are deeper groundwater systems that might be perhaps interacting with the meltwater or important in other ways. So as I say, there's really just been this one study, which is a really, really nice study that just came out earlier this year. This was led by Chloe Gustafsson and was part of her PhD at Lamont. And they were working in West Antarctica, just inland of the Ross Ice Shelf, in a region where there were known subglacial lakes. So there was radar data and other data that there were known subglacial lakes there. And they did an MT deployment over these lakes to investigate the lakes and then also the deeper groundwater system. And so these are their results. This is kind of what MT models look like. So here we're looking at looking down into the Earth. So here we're looking down to 5 kilometers depth. So kind of a cross section through the Earth. And we're looking at the electrical resistivity of the Earth. So in this color scale, the yellow colors are more resistive, so places where it's harder for the current to flow. And the blue colors are more conductive, where it's easier for the current to flow. So we have at these greater depths here, we have...
No, I'm good, thank you. No, not a coffee drinker. Thanks.
Some people, I think, need to mute their microphones. If everyone could just check that they're muted. Thanks. So we have some deeper bedrock that, as you can imagine, is more resistive. So these yellow colours, it's just, if it's just crystalline rock, it's going to be hard for electricity to flow through it. And then as we get to shallower depths, we get into a sedimentary basin, which is more conductive. And we might expect that if you've got sediments that has a lot of pore water in it, then it's easier for current to flow through those sediments. But what they saw that was very interesting was that the conductivity, and you can see it particularly in this top model, the conductivity actually increases with depth through this sedimentary layer. So we kind of get to darker blues with depth. And so their interpretation of this was that we've got this basal melt forming the subglacial lake just beneath the ice, and that's going to be fresh water, which is actually going to be quite resistive. And as we get deeper into this sedimentary layer, down to sort of 2 kilometers depth, then the salinity increases and increases the conductivity of that pore water that's in the sediments. So their interpretation of this is that there's this basal layer that, as I say, is this freshwater, meltwater from the ice. And then there's a deeper groundwater system that is more saline from the paleo seawater. So as we go with greater depth, then we see it being more conductive. But that there's a gradation between those regions, that there's some interaction between this shallow basal melt layer and the deeper saline groundwater. And so that has a few implications for our understanding of the hydrologic system and its impact on the ice sheet here. So again, it could mean that because we have this basal melt layer that's seeping into the deeper groundwater systems, that as those groundwater systems maybe are lost out at sea, then that's unmonitored loss of meltwater. And there's also the potential that because those systems are linked, that maybe that deeper groundwater, which is likely to be hotter, could be advected up close to the base of the ice sheet and increasing the heat there and helping to melt the ice there. And that's certainly some of the places that we have the highest surface heat flows are places where there's really active hydrologic systems. You just need to think of a hot spring where there's hot groundwater that's coming up to the surface. If we have that beneath an ice sheet, then obviously that's going to be helping to melt the base of the ice sheet there. So really important things to be looking at, and as I say, kind of a new application of this technique. But yeah, something that's going to be really interesting to look at over more glacial systems to see if we can put more of that picture together of how the whole system is working together to get a better understanding of those dynamics. So that's sort of the shallower investigations, and now for most of the rest of the talk I'll be talking about looking more deeply into the Earth, and this is the bulk of what my previous research has been focused on, and again something that we'll be doing with the ACEAS fieldwork. And so this is really addressing this question of glacial isostatic adjustment, or GIA. And so to understand what's going on with GIA, we need to understand a bit about how the Earth works. And so on the Earth, we have really the plates, the sort of the brittle outer layer of the Earth that's quite coherent, that would often be referred to as the lithosphere, but it's really, they're basically the same term, the plates. And then as you get deeper in the Earth gets hotter, and the mantle then deeper in the Earth is then more ductile. So it's not liquid, it's not like magma down there, but it's a very, very slowly flowing solid, but it can slowly flow. And the Earth is really dynamic. So there's always tectonics going on. There's subduction zones, there's big convection cells in the mantle. And then near the surface, there's mass changes, there's, you know, mountains eroding and things like ice sheets forming and being melted. And as this dynamic system is always being dynamic, it's always seeking to be in gravitational equilibrium. So I've got a picture of an iceberg here. You can kind of think of it as analogous to an iceberg, where if the iceberg was our kind of brittle plate, if you imagine you knocked a bit off the top of the iceberg, it's going to shift so that it's in gravitational equilibrium. The way that it's not like an iceberg is that the iceberg's just floating in water, and that shift happens instantaneously in water. But in the Earth, because the mantle has a really high viscosity and it doesn't flow instantaneously like water, it just oozes extremely slowly, it takes a long time for this isostatic equilibrium to be reached. And so for glacial systems, this takes on the order of a few thousand years for this isostatic equilibrium to be reached. So if we look at that in some cartoons, so even initially when there's an ice sheet sitting on the Earth depresses beneath that ice sheet and bulges out around the sides of the ice sheet. And then gradually as that ice sheet melts, then, as I say, that reverses. The bulges around the side start to collapse, and the depression beneath the ice sheet reduces. So often think of it like a person sitting on a mattress. You sit on the mattress depresses beneath you, and you stand up and the mattress rebounds. But it's actually even more like being on a memory foam mattress, where there's a time lag before that rebound happens. So great. So why do we care about this? And indeed, you know, and this is an issue that people have been researching for many decades. And until probably not much more than a decade or two ago, this was quite an academic question, just trying to understand more about how the Earth works. But this has become a question that has a lot of practical importance, because we really need to understand this GIA so that we can have accurate models of exactly how quickly ice is melting. And that's because we need this GIA correction in ice loss measurements from gravity grace data or from altimetry data. And that's because as those satellite measurements pass over our ice sheets and measure, for instance, you know, if we had an altimetric measurement that measured that our ice surface, in an exaggerated example, if our ice surface had decreased by 10 centimeters, but if our Earth surface had rebounded by 5 centimeters, then that brings in a massive error into that calculation of how much ice loss that altimetric difference accounts for. So that's an exaggerated example, but it is, it's an uncertainty in those those gravity and altimetric measurements that we need to correct for. We do have measurements, so GNSS, GPS data on bedrock give us measurements of that surface uplift. But that surface uplift, there is a kind of an instantaneous elastic component to the uplift, and then this long-term viscous component. And to understand exactly how those GNSS data relate to current ice melting, we need to be able to separate those components. And so all of this just brings an uncertainty into our ice loss calculations, and then also our sea level rise predictions. And the sea level rise predictions, not only in terms of the uncertainty of the ice loss, but also in the region, at least the region proximal to the ice sheet itself, that Earth's surface is changing. So to predict what the sea level rise is going to be in those places, we need to know how the Earth's surface is going to change as well. So this is something that we need to understand. And our challenge is that there are few constraints on the magnitude of the Earth uplift in Greenland and Antarctica. And as I say, so we have those constraints from GNSS data, but they need to be on bedrock. So once we get to beneath the centres of the ice sheets, we can't make any of those measurements. And apart from that, this is not something that we can measure directly. So our solutions to improve this data, we need lots of GNSS measurements. The other part of this, because we're looking at the response of the viscous response of the Earth to what has happened with the ice sheets over thousands of years, we also need reliable ice sheet history models, so we know how the ice mass has changed over those thousands of years. And then the third part of this is that we need to understand what the mantle viscosity is, because that's going to determine basically how fast it's rebounding. If the Earth is really, really strong and really, really viscous, it's going to rebound much more slowly. And if it has a really low viscosity, it's going to rebound much more quickly. So we need those two components. We need to know what the ice sheet has done in the past, and then we need to know how strong the Earth is as to what its response to that will be. And so that's the kind of the aspect that I'll be talking about today. And to produce the best models of mantle viscosity, again, this is not something that we can measure directly. So we need to use geophysical data, and really just we need to, because one of so many things in the deep Earth are just, it's like being a detective on a crime scene where you don't have enough clues. You just have to take what information that you can get and really make the most of it and figure out how all those bits of information work together to give you the best answer possible. So really the geophysical, the ways that we can measure the mantle is with seismic and MT data. So we really need to pull the most out of them that we can to get the best constraints on mantle viscosity that we can. So currently, GIA is absolutely accounted for and is a component of ice loss models. But currently in those models, that GIA those GIA models need to be improved. So currently most of those models assume that the Earth viscosity is kind of 1D. It's pretty homogeneous. Laterally, it's just layers that are homogeneous across those regions. But we know that the Earth is really complex and varies a lot laterally. And its viscosity is likely to vary a lot laterally as well. So this is just a model from Greenland showing the comparison between, so those kind of 1D assumptions that are in a lot of current models, the comparison in the uplift rate that we would measure of the Earth's surface from those 1D models, and if we allow the Earth to actually change in viscosity in 3 dimensions. If we allow those 3D variations over different depth ranges. And you can see these are really significant differences in modelled uplift rates. And so these 3D variations in this model are taken from seismic models and converting those into viscosity. So even from these, this is just a this is just a kind of a forward model. Even from these, you can see that it's important that we account for those 3D variations. In Antarctica, these are seismic velocity models of Antarctica. There's absolutely no doubt that the mantle properties vary a lot in 3 dimensions across Antarctica, and it's especially with a huge difference between West Antarctica, with these red colours, which are slower seismic velocities because the geology there is a lot younger and hotter, and East Antarctica with blue colours, which are much more seismically fast. On a base level, we would expect, therefore, that East Antarctica, if it's really colder down deep in the Earth, it's likely to be stronger and more viscous. West Antarctica is likely to be hotter and less viscous. But also interestingly, so these are the seismic stations from which this model was produced. Really, as with everything, there are a lot more measurements in West Antarctica than East Antarctica. So even these seismic models are much, much better constrained in West Antarctica, and really an illustration that we need a lot more data in East Antarctica. And then these are viscosity models calculated from those seismic data. Again, just showing that that really strong difference in viscosity, certainly between West and East Antarctica, and then within those regions as well. And then again, the calculations of uplift and the different calculations of uplift that we would get if we just assumed a 1D viscosity. Look, this isn't even accounting for all of the mantle viscosity. This is just looking at the thickness of the plate. If we had a 1D model versus a 3D model, and again, really significant differences in uplift rate if we account for that 3D, those 3D viscosity changes. But also I point out in this model, they haven't even kind of calculated that for most of East Antarctica because there's just not enough data there. But then I would say as well, so as I say, all of these viscosity models that we've been looking at have just been calculated using seismic data. And so this is going back to that Greenland model and a comparison then between those modelled uplift rates and what we observe with GNSS data. So the observations are the black circles. 1D models are with the open circles and the 3D models are with the coloured circles. And you see that actually none of it is matching the data well at all. So we need to account for these 3D viscosity variations, but we also need to just improve our viscosity models and have better input into these things. So how do we do that? And how are we calculating this viscosity at all? As I say, so viscosity is not something that we are able to measure directly in these places. All we can do is go from our geophysical data and then make some calculations to then calculate what the viscosity must be. So we have our geophysical data in the examples that we've been looking at, that's seismic data. We add into that geophysical data some mineral physics data. So this could be, this is experimentalists taking, for instance, an olivine crystal and putting it under really high pressures and temperatures like you would get deep in the earth, and calculating what its seismic velocity is. Testing that over slightly different compositions, slightly different temperatures, to see how temperature and composition relates to, in this example, seismic velocity. So then we go from our geophysical data, combine it with our mineral physics data and get an interpretation of the temperature and composition of the Earth. From that, we then include more mineral physics data. So then people looking at those same minerals and then putting them under stress and seeing how they deform and what their viscosity is, to then go from our temperature and composition we've calculated of the Earth to then what its viscosity must be. But there's, as you can imagine, there's a lot of uncertainties in this. There's uncertainties in all the data sets, but there's also trade-offs. So there's not there's not one, if we measure a seismic velocity, there's not one specific temperature and composition that corresponds to. There's a trade-off between those parameters. So there's uncertainty in exactly what that temperature and composition will be. So by adding in more data types, we can basically produce more constrained temperatures and compositions of the Earth, because each of those things have their uncertainties and their trade-offs, but when we combine them together, then some of those cancel out and we get a better constraint of Earth temperature and composition, and then from that we can produce a more accurate Earth viscosity. So in our example, looking at these upper mantle depths, where our geophysical data sets, we have our seismic velocity and electrical conductivity from MT. So they respond to slightly different things. They both respond to the temperature of the Earth. So combining them can improve the constraints of the temperature. They both correspond, they both are affected by if there's partial melt in the Earth. And then slightly different compositional effects. And really importantly, the electrical conductivity is quite strongly affected by the hydrogen content of some minerals in the mantle, which is also a thing that really strongly affects its viscosity. So by combining these two types of data, we can produce more accurate models of Earth viscosity. So these are some results from a PhD student of mine, Florence Ramirez, who's at the University of Oslo. So this is a paper of hers that just came out a few weeks ago in JGR. And in this, I guess we were really hoping to quantify some of that we could understand that, okay, combining seismics and MT data should help improve our estimates of mantle viscosity. And we're really hoping to quantify exactly how much it improves it and how well we can estimate mantle viscosity from these geophysical data sets. So this, I'll kind of talk through this figure because there's quite a lot going on. So all of these plots have temperature on the horizontal axis, and the water content of the minerals, as I say, really affects its viscosity on the vertical axis. And we have a lot of different contours. So I'll say firstly the shading. So the minerals deform in slightly different ways depending on their conditions. So the shading just refers to those. If that can be ignored for the purpose of this, but if you're interested in it, happy to talk about it. And Florence's paper is a good place to learn about that. So the contours we have here, we have these blue vertical lines, which are seismic velocity. And you can see they're just, they're vertical. They don't change with water content because the seismic velocity is not affected by the water content. Then we have these dashed grey lines, which are the viscosity. So we're imagining here we just have a seismic velocity that is between 4 and 4.5 kilometers per second. And from that, we can use those mineral physics data to estimate this temperature range that we could possibly have. And then that corresponds to the viscosities within that range. If we only have MT data, so here again, we're imagining now these purple curved contours are electrical resistivities from MT. So again, we're just imagining we have measured a resistivity with uncertainty between -2 and log -2, -3 ohm meters. Here we see this region does change with water content. And again, with that, we would have this grey shaded region, which corresponds to a region of viscosity that we could possibly have. When we combine them, then that shaded region basically decreases in size. So we've decreased the range of viscosities that are possible with those two data sets. And in this is purely a theoretical example. If we had measured the same seismic velocity but a different electrical resistivity, then that that possible region of viscosity then gets shrunk down even more, just showing, yeah, that combination, depending on the Earth conditions, can really tighten those viscosity constraints. So then Florence kind of ran these calculations over a lot of different velocities and electrical conductivities. So that's what we're seeing here, velocities on the horizontal axis and electrical conductivities on the vertical axis. And showing that then basically if you had a data set that you had measured those two things, you could sort of go and see what's my possible viscosity, and also the uncertainty in that viscosity, that, and this is in a log scale, that basically, like we're seeing in the previous plot, if there's a pretty solid agreement between what those two data sets are showing, then there's still a relatively large uncertainty in that viscosity. But if there's a bit of an offset, then we can produce a much smaller uncertainty in that viscosity. There's a lot in Florence's paper, and she tests a lot of other factors, including how the composition of the Earth affects those data sets, how things like stress and grain size affect those data sets. That's kind of too much to go into today. But one important finding of that is that really, like in regions of lower stress, that viscosity uncertainty decreases quite a lot. So so here she's basically run sort of a cratonic example, which is the type of geological system that we're in East Antarctica, where things are a bit colder, there's lower stress, compared to a more geologically active region where there's higher stresses and higher temperatures. And the uncertainty in the viscosity that we can produce by combining the seismic and MT data is kind of lowest in those cratonic regions of lower stress. So that kind of bodes well for work that we might be wanting to do in East Antarctica, of just how well we can estimate the Earth viscosity from these data sets. And I would say this was a figure that I was going to put in half an hour ago and forgot to. So I already showed you that we don't have many seismic measurements in East Antarctica. We have basically no MT measurements. So yeah, I did a survey in Prince Bay in about 2008. And you know, like that's, yeah, there was a survey kind of going across the Transantarctics, which just goes into East Antarctica. But that's basically it that we have. So so it's really important to bring in MT data to improve these viscosity constraints. And the first step in that is just to collect some MT data. We really don't have much at all. So any measurements that we can make are going to be a massive step forward in improving these viscosity measurements. I'm very quickly going to go through, this is sort of a case study of this work where I collected MT data in Svalbard. So Svalbard, there are some estimates of what the mantle viscosity there is from looking at sea level change and models of past ice sheet behaviour. But those ice sheet models there are a bit uncertain. So this is kind of the range of models of mantle viscosity from Svalbard, and as you can see, it's quite a large range. So we collected some MT data. There is already seismic data and some other data that kind of constrains the thermal structure of the upper mantle. Here's our MT model. Here, going from the yellow colours being more conductive at greater depths to the blue colours here in the plate region being more resistive. And we ran some models to test. As I said, there's uncertainties in all of these steps, going from the geophysical observations through to temperature and composition through to viscosity. So we ran some genetic algorithm models to test those trade-offs. And basically what we found was that in all of these models, they required there to be a layer with some partial melt in it just beneath the plate. And so that's going to mean that's a very low viscosity layer just beneath the plate. And then we're also able to measure the the hydrogen content going down to greater depths and the temperature going down to greater depths. So from those, we've then produced these two possible models of mantle viscosity, and the two models come from using different experimental constraints. But you can see kind of agree quite well with the older estimates from the sea level data at greater depths, but none of those previous models included this very low viscosity layer just beneath the plate. And one thing that's kind of still open after this work is that I would love it then if a GIA person went back to this and tested if including this low viscosity layer in the models would help constrain even the ice sheet history models, that then only some ice sheet history models actually match with what the Earth viscosity data show. And to finish off with, I'm going to talk about this, this work I've just been doing in Greenland, which is addressing exactly these same questions. So, so Greenland, we have seismic data, and we definitely expect in Greenland as well for there to be a lot of variations in mantle viscosity, partly because a lot of Greenland is very old, it's likely to be cold and quite stable and strong. But the Iceland plume passed beneath Greenland somewhere between 50 and 100 million years ago. And it's likely that that plume track is still hotter and has a much lower viscosity. So we expect there to be these lateral variations. This is the work that we did. We started out kind of with a pilot study in 2018, just at Summit Camp, which is in an NSF camp in central Greenland. 2019, we went to Eastgrip, which is an ice drilling camp in the northeast. Did an array around there with a lot of great hope that we would go back in 2020 and finish all the work. And of course, that kept getting cancelled and delayed until thankfully, finally, this year we were able to go back and then collect this really huge data set across much of the rest of Greenland. So with this, as I say, I'm only back 3 weeks, so I don't have results from this yet, but we're really hoping that we'll be able to model those viscosity variations across Greenland. And this was, there were no MT data collected on the Greenland ice sheet before this work, so this is really kind of new stuff. Just I thought I'd talk a little bit about what it's kind of expecting that a lot of people here today are mainly Antarctic people, and there's certainly not a lot of Australians who seem to work in Greenland. So I thought it's just a little bit about what it's like there. In some ways, it's much easier than Antarctica because you can just fly there. So Kangerlussuaq is the main airport town that you can commercially fly there with Air Greenland. It has a, if anyone's had the misfortune of going to McMurdo, it has a kind of feel of McMurdo, of being kind of in a beautiful place, but a kind of a big dirty town, and it's really just the airport town. But like McMurdo, you only need to go a little bit out of town. Here we're testing some instruments before we went in the field, and it becomes quite beautiful. And you can also drive, sort of for an hour from there and head and be on the edge of the ice sheet. So there's quite a lot of science that happens out of Kangerlussuaq, just on the edge of the ice sheet, and there's a glacier there. Summit Camp is really the main research station, the main permanent research station on the Greenland ice sheet. So this is an NSF camp. All of the research flights really are done by the US Air National Guard. But there is also, you know, because there's commercial flights there, it is also possible to charter an Air Greenland flight or helicopter to do work. This is like a really nice camp. There's probably 40 or so people there in the summer, 5 people winter. And they have a lot of permanent, really long-running science that goes on there, a lot of atmospheric and snow science that goes on there. So these were some atmospheric scientists giving a talk about the science that they were doing while we were there. And it's a kind of place with, you know, there's mechanics and carpenters and all of those really useful people in polar regions. So that was sort of the last place that we were working. Then Eastgrip Camp which is where we were in 2019. This is a fascinating place. This is an ice drilling camp. So it's a semi-permanent camp, and this dome structure is used for a lot of ice drilling around Greenland, and it's actually portable. So it's on skis and can be towed from one place to another. So it's been at East Grip for, I guess, about 5 years or so, but has been at other places at the ice sheet previously. And at East Grip, all of the drilling is done underground. So they have this kind of tunnel going down under the ice. And the drill is down there, and then all of these scientific laboratories then also in these tunnels underneath the ice so that the work can continue regardless of the weather. It was a really fascinating place to be for me to learn about a lot of ice core science that I didn't know anything about. It was, yeah, it was great. So that's their focus, but they have a lot of other science that comes and goes as well. And then the other place we were working this year was a place called Raven, which is again a US-run camp, but it's really just a skiway with a couple of people looking after the skiway, and really fascinating. Two things that were really fascinating about it. It's where a lot of skiers pass through there when they're doing when they're skiing across the Greenland Ice Sheet. So here, this was a random group of skiers that we encountered while we were in the field. And it's also originally there because it was a radar base run by the Americans in the Cold War. So this radar dome is still there from the Cold War era. For us in this work, so the logistics, at least for my work, have been quite different from Antarctica, because this work was funded mostly by the Norwegian Research Council. And so we had to work with the NSF, but basically I just had to get an agreement from the NSF that they would support our research. And then we would basically pay them back for those costs of supporting the research, but we were not an NSF project. So that meant that then a lot of the, there was logistical support, but certainly not as much as if you were running an AAD program. So we used snow machines, all the way, like I had to buy these snow machines and figure out the fuel mileages and buy all the food and figure out all of those things myself, which in some ways there's certainly a lot less bureaucracy, but then also a lot more responsibility, for instance, to make sure we had enough food out there to keep us alive. So we were working from snow machines. That was, I got to say, that was a nice luxury to be able to do. Hard work. We ended up driving 4,200 kilometres this year, so it was a lot of sitting on snow machines. But certainly compared to using aircraft, means that you can just work in a lot more weather conditions. So we had the snow machines, we had all of our gear that we towed behind them. And we were mostly just in tents. So we were using these bases as kind of hubs, but then going out on traverses and camping out on the ice. So yeah, we had a couple of tents that we were mostly in, and also some beautiful sun halos. One challenge of being in the Arctic is obviously that you have to worry about polar bears, which so we sort of always had to have a rifle with us and a lot of bear safety around the tent as well. I guess that's the biggest worry, that bear is going to come during the night while you're asleep. I'm actually collecting the data on ice. So collecting the data is basically with a magnetometer that measures the magnetic fields. Electrodes that measure the electric field. So these are out here, we're about 50 meters spacing between the electrodes, north, south, east, and west. And then a logger box powered by a battery and a solar panel, and then just a data logger that collects all of those data. And for those deployments looking into the mantle depths, that instrument stays out for at least a week, ideally a couple of weeks. But it means that within the context of one field trip that you can deploy the instrument and then go pick it up and get the data as well. So it's not like a seismic deployment where it might need to stay out for a year before you can go, a year or more before you can go pick it up. So yeah, as I say, that's those experiences in Greenland. And yeah, I've never really been sure why so few Australians work in Greenland, but it's, you know, a lot of the questions are really similar to Antarctic questions. Yeah, a lot of the logistics of getting there and doing the work, simply because you can just get on a plane and fly there, are much easier. And there are some really fantastic groups of people over there who can help do work. So if anyone's interested in thinking about Greenland projects, please feel free to talk to me for any advice on that. So as I said, we've just got back. I don't have any results from that. So our next steps from that work is to first process and model the data we've collected to produce a conductivity model. And then kind of using those examples from Florence's work, then we combine that conductivity model with the seismic data that already exists and calculate the viscosity. And then the other whole part of that Greenland project is that my collaborator on that, Clint Conrad at the University of Oslo, is then working on updated GIA models that allow those 3D variations in mantle viscosity to be an input into the model. For ACEAS, then kind of all of these ideas are then what we plan to take to ACEAS. So this is a map. Obviously there's no, I realize there's no location data at all on this map, but these are the Bunga Hills, and extremely preliminary ideas of where and how we might collect some data. So, but the hope is that we'll collect some broadly spaced MT data that will look down to those mantle depths that we use to constrain mantle viscosity in this region, and collect some profiles of shallower data across the Denman to look at that basal melt and groundwater systems and how those are interacting. So yeah, thank you very much for your time.
Thank you so much, Kate. It was a great seminar, and I apologize in advance for my internet connection. Are there any questions for Kate? Nobody?
Laurie, I've got one. Matt King here. I've got two actually. So Kate, one of the things I think that you said messes with the nice story around resolving the water content and the viscosity is partial melt, I guess, within the crust or the base of the crust, I guess. So what do we know, or what's likely to be the situation in East Antarctica with partial melt? Is that very unlikely or unknown?
I mean, I guess it's unknown because, you know, most things are unknown, but I'd say it's very unlikely that we wouldn't expect in such a kind of tectonically stable region. Certainly within the lithosphere, we wouldn't expect there to be any partial melt. And then I guess potentially, and then this is then kind of globally unknown in geophysics, then when we get deeper into the upper mantle, whether there's partial melt there. But we wouldn't expect it, and there's no indication really, so far as I understand from the seismic data, that there's that there are, you know, particularly regions of particularly low velocity that would be suggestive of partial melt, is my understanding.
Okay.
But also, like, melt then is a strong response in both seismics and MT. So if there is melt there, then we should be able to figure it out.
Okay. And the other one's a bit more speculative, but thinking of the oceanographers. So if you do MT on a floating ice shelf, what does that tell you about the ocean currents beneath the ice shelf? Can you get anything useful?
Wow. That's okay, so I guess the short answer, that's probably obvious from the long pause, is that I don't know. You know, you would see, so obviously seawater is conductive, and if the seawater is flowing, then you would see a signal from that. And I guess there would be a difference in that signal depending on exactly how that current is flowing. But I reckon it would be, I think it would be a very difficult, there'd be much easier ways to understand the current than that. Yeah, I don't think it would tell you very much useful information. What's probably more useful would be, and then this is maybe not so useful for the oceanographers, but doing, taking measurements on the sea floor that are then still, again, looking at that groundwater system. So then what would be really nice would be to be able to go across, do sort of an onshore, offshore survey across a glacier, where we could then ideally track that basal melt and deeper groundwater system and see how it moves offshore and what that water does. That, which would also be, yeah, that would be challenging, but I think it would be possible to collect those data.
Thanks, Kate.
Yeah, we do have another question from Nathan Bindorf in the chat. So I'm going to read it out, but would a local seismic array in the Denman region capable of 5 kilometer depth ranges add to the planned MTs that you showed in the next step?
Yeah, so I think, and I guess one of the other things that I didn't say that we have also been doing in Greenland, so that East Grip camp, so that's actually there because it's on an ice stream, the Northeast Greenland ice stream, which is a really unusual, very fast flowing ice stream that goes very far into the ice sheet. So they're drilling to understand what's going on with the ice. And then there's a lot of radar data looking at basal melt, and also shallow seismic data looking at the sediments and trying to understand the meltwater in those sediments there. So that's it. We also, when we were there, collected a bit of MT data across that ice stream as well, which again, I also don't have results of that yet, but that's going to be, that combination of things in that setting is really nice as well, to be able to combine that shallower seismic data with the shallower MT data, and ideally radar data and gravity data, and really every other type of data that we can get, to then combine those and get a much better constraints on, you know, where are we seeing basal melt, where are we seeing saturated sediments, and maybe what's the difference in composition of the water in those sediments. So that could certainly be that could certainly be advantageous to have those seismic data at that depth range to compare. Mm-hmm.
Okay, well, thank you so much, Kate. I think you said you had to go, so
yeah,
we will
sorry.
ask you after you can. And if you have a question, maybe contact Kate directly. Thank you so much for a fantastic seminar. Our next seminar is next month, the 17th of August, and will be given by Tom Williams at UTAS. So thank you so much, everyone, for joining in, and see you next month. Bye.
Thanks.
Thanks, Kate. See ya.